Hello, Shaler area, and welcome back. This is the Unit 1 note video number 3. We're going to pick up right where we left off with step 4 of the scientific method. And this is take 2, because the first time I did this video I messed up around the 7-minute mark, so I had to start all over again. Alright, so let's review briefly what we did in the last note video. We talked about the first 3 steps of the scientific method. Step 1 is ask a question or make an observation. And step 2 is to make a hypothesis. And remember, a hypothesis is pretty much going to be an inference of some type. It should be written in the if, then, because format. And the best definition is a testable explanation, or something you can test. Step 3 was actually doing the experiment. And when you did the experiment, you had to make sure you had a control group and experimental groups, and you had to make sure that you were keeping straight your independent and dependent variables, or your manipulated and response variables. So you did that experiment, you have all the observations written down, all your quantitative observations are recorded in your data tables. Now what is it that we are going to do? We're going to do step 4. We're going to take a look at this data. This is where you look for patterns. When you're actually doing the experiment, you kind of want to don't let yourself try to analyze the data until you're done, or else you might start manufacturing some data. So get all the raw data and then start looking for the patterns. So in this experiment, remember this made-up experiment about me trying to have a better garden of tomato plants. I've decided to measure the height, which is the response variable, of the tomato plants every 3 days. So I'm doing it every 3 days because, you know, plants don't grow very fast, so measuring it every day might just be more data that I need. And also I have a life, so I don't want to be out there measuring plants every single day. I'm going to do it every 3 days. So also, there's 10 tomato plants in each group. Instead of writing down all 10 heights, to save a little bit of space on the data table and to make things a little bit more concise and easier to follow, I'm just going to write down the average height of all 10. So I'm going to have one data point for unfertilized plants, one data point for fertilized plants. And here is the data table. When you're looking at a data table, 2 terms, and sometimes students mess them up, is that columns go up and down. So if I say look in the first column or the second column or the third column, then that's where you're looking. And rows go left and right. Sometimes students mix those up. So here we have the data table and a couple of quick checks. So we'll make sure that we go over these questions in class. So quick check number 1. What's the purpose of the day 0 row? It's interesting. Whenever you're recording, how many of you record something that's like a day 0? It's a really important thing to have in your experiment and in your data. And secondly, let's see how well you can just read the data table and find information. How many days did it take the unfertilized plants to become 36 inches tall? So one group will have to answer that one in class. Alright, so we have this data table. It's got numbers all over it. In order to put all of those numbers in a form that you can visually see a pattern, we need to make a graph. Graphs aren't something that math teachers have been teaching you how to make just because they think they're pretty or a fun puzzle. Graphs are really, really important. Graphs are a way to take a huge amount of just raw numbers and actually put them in a form that makes the patterns that are in those numbers leap out at you. Makes them visual. So the 3 most common kind of graphs that you're going to see line graphs, you're going to see bar graphs, and pie charts. In science class, you're almost always going to make a line graph. There's only one bar graph that I can even think of that we'll take a look at as the year goes on. So line graphs are pretty much always what we're going to be talking about. And every line graph has the x-axis, which is the one that goes along the bottom, and the y-axis, which is the one that goes up and down. Now when you make a graph, there are specific things I'm going to be looking for on every graph that you make. And we're going to actually spend some time, a couple days in class, working on a graphing homework packet, and you're going to have a graphing quiz. Your first quiz of the year is going to be on graphing. So every time you make a graph, there are 5 things I'm going to be looking for, and they're all going to be worth points. So every graph must have a name that tells the reader what is actually going on. Every graph should have data points, and that's the easy part. You guys are good enough now that this is something that you generally don't mess up. The scale. Some students struggle with this one a little bit. You might actually not be familiar with the fact that it's called a scale, but you'll see on the graphs when we talk about it that you'll realize what that means. Axis units and axis titles. Now, a key is a sixth thing. All right, so if, let's say you have a quiz and there's a question on the quiz, what are the 5 things you need on every graph? Key would actually not be a correct answer for that, because a key is a sixth thing that you only need sometimes. See if you can think of when you need a key and when you don't. All right, did you come up with something possibly along these lines? Let's see. Ooh, we'll do this one. Sweet. So we have our y-axis and our x-axis, and we might have something that is prices of Pokemon characters after Pokemon Go was released. See, it's going up. Do we need a key for this graph? No. All we need is the title that's up here, and it would tell us exactly what it was that we were looking at. We don't need a key on this graph. But if I do this, now we need a key, because we don't know which line is actually telling us what. So whenever we look at the 5 things that you need on every graph, these are the 5 things that you need always: name, data point, scale, units, and titles. You only need a key when you have more than one line. Alright, so here's a graph made from that data table. We're going to go through these the questions that are there. Actually, if you should maybe pause for a second, pause the video for a second, that's what I would suggest, and answer the questions, and then start the video back up again and see if you got the answers right. That would probably be the best way to go through the notes. All right, I'm going to assume that that's what you did. Here we have the name of the graph. Now this one might seem silly. It seems silly that I'm going to make such a big deal out of the name of the graph, but it's actually the most important part of a graph. If you don't have a good name, it doesn't really matter what's going on down here, because no one's going to know what it is that you're talking about. So it's also, because the mechanics of making a graph, plotting and connecting the dots, students tend to be very good at. This is honestly the part that students tend to struggle with the most, is coming up with a good name. If this was a graph that an 8th grader coming into class would make, the most common title that I would see on it, an 8th grader would probably write something on here like height versus day. It's very common for students just to write the 2 labels on the axes. But that's not nearly enough information. And it's already written here. Why would you write it again up top? All right. This should be more like a sentence instead of just listing 2 things, height versus day. And at the very least, it needs to mention the 2 groups in the experiment. So it needs to mention your control group and your experimental group, or it needs to mention the independent and the dependent variable. So here, this one talks about the 2 groups. We have the unfertilized group, which, if you remember, is the control group. You have the fertilized group, which is the experimental group. And it has what we're measuring. So it doesn't, this is your response variable. And then as an added bonus, it tells us what kind of plants we're talking about. There's a lot of information in this title. And when you sit down to make your graphs, just keep those things in mind. It should really tell the reader what it is that's going on in the data. So that's the name. What's the title and unit of the y-axis? Well, the y-axis is the one that goes up and down, so that's going to be height is the title. The units are centimeters. Sometimes students kind of balk at what a unit is. They say, yeah, I know what that means, but then when you ask them to explain it, they have a tough time doing that. Essentially, units are what you would say after you would say the number. So if I wanted this to be 40 candles, candles would be the unit. If I wanted it to be 40 years of my life would be the unit. So whatever word you say immediately after you say the number, that's what the unit is. So what's the title and unit of the x-axis then? Well, you might be looking at it going, it doesn't have a unit. It just has a title. But what's the title and the unit? Think about it. The title is day. Well, what would the unit be? What is the word that I would say immediately after saying this number? I would say that this was 3 days. So in this case, the title and the unit are actually the same thing. You don't have to write it twice. That would be redundant. Here's the scale question. So when I ask this in class, students genuinely, intuitively know what the right answer is. But you might just not be sure because it has this weird name of a scale. The scale on the y-axis, up here, if I were to ask this in class, sometimes students would tell me the scale was 44. That's not the scale. That's the upper limit. The scale is how much each block is worth. So how much height, how many centimeters do we go up every time we move one block? And that would be 2. So the scale on the y-axis is 2 centimeters. What is the scale on the x-axis? The scale on the x-axis would be 3 days. Now don't confuse that with this, because here, let me alter this for a second and ask the same question. Come on. Sorry, trying to manipulate this a little bit. There we go. So I was trying to make the numbers disappear. That wasn't as easy as I thought it would be. Alright. Sorry, that took longer than I wanted it to. Alright, I'm going to ask the same question now. What is the scale of the x-axis? Sometimes students want to now change their answer to 6 days, but that's not right. The answer is still 3 days because still each block is worth 3 days. So don't confuse scale with what the numbers count by. And that's where students will sometimes get messed up. Scale is not what the numbers count by. It's not 0, 6, 12, 18. Scale is how much each block is worth. So don't miss that when the quiz time comes. Let's catch back up to where we were. Alright, what is this thing? What are these shenanigans going on right here? This, it's usually 1 or 2 people in each class that knows what it's called. This is called a break. Here's the thing about a break. Don't use one. Ever, 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 ever. No, don't use breaks. Somewhere along the line, a teacher told you that if you want to skip a bunch of numbers, that you can make this little jiggly symbol on your graph, and it's fine. That is a terrible idea. Graphs are so important because of the shape that they show the line. The shape of the line is what you're making the graph to see. It's also why we have to have a consistent scale, because if I was counting by different sets of numbers, it would change the shape of, so if I counted by 2 and then 7 and then 9 and then 1 and then 100, this line would have a different shape and it would defeat the purpose of making the graph. because the graph is all about the shape. So when students think that they can do this, sometimes mistakenly, they do it in the middle of the line. They'll jump and skip a whole bunch of numbers and just put a little squiggly thing there and think that that's okay. That can change the shape of the line. So there is no reason to ever use a break. Now the reason that people want to use a break is because you have picked up a misconception that you have to start at 0. There is no rule in graphing that says you have to start at 0. That wouldn't make any sense. In graphing, you start with whatever number you want to start with. So if our data starts at 30, you could start at 30. You could put 30 on this bottom line right here if you want. In this case, we would get rid of that little squiggly line, and that bottom line would just be 28. And then we count by 2s. This bottom, the origin on a graph that you make with your data, does not have to start at 0, 0. That is a fallacy. All right, so how tall were the unfertilized plants after 15 days? This is a really important skill. You really need to be able to read graphs answering this type of question. So you would find 15 days, you would go up until you hit the line for unfertilized plants, you'd shoot over, and then read the height. Same question, but backwards. How many days did it take to fertilize plants to reach 40 centimeters tall? Well, you would find 40 centimeters tall on the y-axis, go over till you hit the line, and go down, and there's your data point. Now, these are fairly easy questions because I realize you could have just looked at the data table as well. But the reason we make graphs, the other reason that we make graphs, is because when you make a graph like this, I didn't have to go measure those tomato plants every day. I'm still getting accurate data, even though I measure them every 3 days. But let's say, for some reason, I needed to know how tall the plants were on day 10. That would be tough for me to figure out with the data table. But on the graph, if I wanted to know how tall they were on day 10, I would just go to where day 10 was. It would be right about here. Oh, sorry. What's going on? Draw a line. There we go. Day 10, it would go up, it'd hit, and then I'd go over. And right there. You could estimate it about, it's 33 would be in the middle, so that would be about 32.5 centimeters on day 10. I didn't measure it, but that's pretty accurate on how tall it would be. All right, here is the question. So I've done the experiment, I've taken the data. It's important, I'm hoping that you know, that it's important that you repeat trials in your experiment, that you do experiments more than once. So how many times should you do an experiment before you think that your data is good? One is always a bad idea. You should always repeat your experiment at least once. So does that mean you do an experiment twice? The most common answer when I ask classes this question, some students will say 3. And I would say, is there anything better than 3? And they go, 4. I go, is there anything better than 4? And they'd say 5, and then they go 10, and then they go 100, and then they would start to make up weird numbers that don't exist because they sound big. So here's the answer. You can't do experiments an unlimited number of times. You should do them as many times as possible. So that being said, what limits how many times you can do an experiment? There are 2 things in the real world that limit how many times you can do an experiment. Let's say I was experimenting with elephants in genetics, and I wanted to know how traits got passed down to their offspring. It takes an elephant a couple of years to have a baby, and then that baby has to mature. To wait for a generation, it's going to take me my entire life to just run a couple of trials in that experiment. But if I was working with bacteria that divide every 20 minutes, I could have hundreds of millions of generations probably, or at least hundreds of thousands of generations during my lifetime. So time is the big one. And then in the real world, time is like the limiting factor you only live so long. But in the real world, money is probably the more pertinent for how many times you do an experiment. So how do you know when to call it quits? I realize that for you, if you're doing experiments, at home for class, or if you're doing them in class for class, we generally only do things a couple of times. But in the real world, there is a way to kind of know when you've done it enough. I'm going to put up a graph here and see if I can illustrate it. All right, so when you start looking at your data, let's say this is my graph, and I'm collecting data points on who knows what. And I get a point that's here. And then I get a point that's here. And then I get a point that's here, and here, and here. And I do the experiment again. And the second time I do the experiment, I get data points that go here, and here, and here, and here, and here, and here, and here. Wow, very different data points than what I got the first time. So does that mean I did something wrong? Not necessarily. I do it a third time, and I get data points that are here, and 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 here. Again, man, I can't even get data points to like line up on top of each other. I do it again. And now I'm here, and here, and here, and here, and here, and here. Well, you can imagine if you do this an unlimited number of times, and I keep putting dots out here, that they're going to blend and make one line. It would just kind of be a thick line. Well, there's your pattern in the data. The data is rising up here. In this kind of range, this kind of distance here, the thickness of the line, you can sort of think of as error. So you're always going to be measuring something a little bit off every single time. Or there might be some kind of, weird variable that only happened briefly, like wind, that threw off the numbers a little bit and caused error. So, we still have the trend, we can still see the pattern, and we just kind of have to imagine that the real data points could follow anywhere on that line. And once you start to see that, you can stop doing the experiment. That's when you know that you've done it enough, because you're not getting any kind of craziness going on. And then in science, and I know that I've seen this question come up, kids have come in and asked questions about things like this in like algebra and whatnot, that if you have a data point that's like out here, that doesn't match everything up, we call that an outlier. And in science, we generally just say, oops, and we don't consider the outlier when we talk about the conclusion of the experiment. There must have been something really wrong with that one. But sometimes it's the outliers that actually lead to more questions. How did that happen? And then a whole new line of experimentation. And that leads us to the next booby trap. So that's the end of the note video. Booby trap number 3 has 12 questions. Good luck.